The way that we're going to solve rational inequalities is a lot like solving quadratic inequalities. So rational functions has, two polynomials being divided. So we want to rewrite it so we have 0 on one side, and then figure out what values make our numerator or denominator equal to 0. We're going to use that to break up our number line into intervals and test a number in each interval. One thing we do have to check is to make sure that no endpoints that are included with a less than or equal to or greater than or equal to make our denominator equal to 0. If they do, we're going to have to exclude them because we can't divide by 0. So first off, I'm going to go ahead and get 0 on one side. So you'll have 5 over x plus 4 minus 1 is greater than or equal to 0. I want to pause for a moment and talk about why I subtracted 1 instead of multiplying both sides by x plus 4. Because if it was an equation, you would want to, since you're dividing by x plus 4, multiply both sides by x plus 4. You could get 0 on one side and solve it that way, but you wouldn't have to. On an inequality, I have to. Because if you think about how inequalities work, if my inequality is 5 over x plus 4 less is greater than or equal to 1, if I divide or multiply an inequality by a negative number, I have to flip the direction of my inequality sign. So if I multiply both sides of this by x plus 4, but that includes a variable, I don't know if x plus 4 is positive, I don't know if it's negative, so that would create two different cases, one where it's less than or equal to 1, and one where it's greater than or equal to 1, and I don't really know which one I have. So that's why we're going ahead and getting 0 on one side instead. So do not multiply both sides by x plus 4. So back to our problem, instead getting 0 on one side and getting a common denominator, so I can go ahead and subtract 5 over x plus 4 minus 1. So if I get my common denominator here by multiplying by negative 1 times my x plus 4 over x plus 4, then I can rewrite this as a single fraction of 5 minus 4 would give me 1, plus negative x, or 1 minus x, all over x plus 4 is greater than or equal to 0. Now I can figure out where this is equal to 0 at or undefined at, and use those to break up my number line, because that's where it could switch from being greater than or equal to 0 or less than or equal to 0, kind of like on my quadratics where I figured out where it was equal to 0 and then tested. So it'll be dividing by 0 if my denominator is equal to 0. So that is when x plus 4 equals 0 or x equals negative 4. It'll be equal to 0 if my top, 1 minus x, is equal to 0, which is where x is equal to 1. So let's write a number line and then test values in between those. So if I pick my favorite numbers that are in those three intervals, so a value that's less than negative 4, say negative 5, plug it back into my original and check and see if it makes that inequality true or not. That'll give me negative 5 is greater than or equal to 1, which is definitely a no, so numbers less than negative 4 do not work. Let's try one that is in between negative 4 and positive 1, say 0. 0 is always my favorite. So if I plug that in, I'll get 5 over 4 greater than or equal to 1, which yes, that is. And then let's go ahead and test a value that is greater than 1, say maybe 2. And if you plug 2 in, you're going to get 5, 6 is greater than or equal to 1, but it is not. So my original inequality was greater than or equal to, which means I would expect to include my endpoints for my solution interval, except I can't include x equals negative 4 because that would make me divide by 0 in my denominator. So I have to switch it to a parentheses. Let's go ahead and take a look at this graph just so you can kind of make some connections. So we've got our line y equals 5x plus 4 shown. Our inequality wanted to know where that was greater than or equal to 1, which is essentially where your output values are greater than or equal to 1. So let me shade. In that green region is where my y values of my points are greater than or equal to 1. So if you look at my function, this top part right here, between the x values starting at 1 and then going backwards towards, it looks like, if you look at your denominator, you can't have an x value of negative 4. So between this point at 1, 1, so for the x value of 1 back to the x value of -4, are where my y values are greater than or equal to 1. If I look at x values bigger than 1, or on the other side over here, less than -4, those do not give me output values greater than or equal to 1. So just between -4 and 1. Let's go ahead and take a look at one more. So same idea, we want to get 0 on one side, which means I'm just going to add 5 over 3x plus 2 to both sides of my inequality. You could subtract 5 over x. And then if I'm adding those two rational expressions together, I have to get a common denominator by multiplying my first one by 3x plus 2 over x plus 2, 3x plus 2, and my second one times x over x. And that would, if I distribute, give me 0 is greater than or equal to 15x plus 10 all over x times 3x plus 2, and plus 5x over 3x plus 2 times x. Since those are common denominators, I can now add them together and get 20x plus 10 all over x times 3x plus 2. And now to determine what intervals I need to test values in, let's see where my numerator is equal to 0 and my denominator is equal to 0. So the top will be equal to 0 if I have x equals -1/2. My denominator is equal to 0 if either x or 3x plus 2 is equal to 0. So that's actually in two different locations, x equals 0 or x equals -2/3. So if I draw myself a number line and think about the intervals that I need to test values in, there's actually quite a few of them. So my smallest one, -2/3, -1/2, 0. So that's actually 1, 2, 3, 4 different intervals that I'm going to have to plug values in and check to see if they're part of my solution set. So if I test something less than -2/3, like say -1, I could plug it into my original and see if it makes it true or not. You can plug it into the version that has 0 on one side, but I always just go back to the original. I think it's easier. And that one gives me 5 is greater than or equal to -5. That does work. If I try one in between -2/3 and -1/2, I'm going to have to go with a decimal here since it's -2/3 and -1/2. So -0.6 sounds good. I won't torture you with all of the details. You could plug it in. If you do it in your calculator, make sure you put the denominator of your fraction in parentheses. That does not make it true. I'll test a couple more in the other two intervals. By the way, there's not really a pattern to these, like on your quadratics, you knew it was either the middle or the two outside ones. Rational functions don't have like a standardized shape like that, so you do have to test a value in every single interval and check. No shortcuts. So I ran through tested values in all 4 of those intervals. This is a greater than or equal to, but again, you can't include any values that make your denominator equal to 0. So I can't include 0 or -2/3. So I'll go ahead and use a parentheses on my -2/3. And then the numbers from -1/2 to 0 worked, parentheses on 0.